So, Tetsuya, please start.
Okay. Hello everyone. I'm Tetsuya Hashimoto from National Tsinghua University in Taiwan. Thank you very much for giving me this opportunity to talk about our recent research. Today I'm going to talk about revealing the cosmic reionization history with first radio burst in the era of Square Kilometre Array. So my talk is based on recently submitted paper to monthly notice, which is done in collaboration with these people here. So one sentence summary of my talk today is a new method to reveal the cosmic reionization history using future first radio burst. So this is very simple. Let me get started. So the cosmic reionization history is one of the biggest phase transition of the universe from neutral to ionized states. So this reionization is supposed to happen at very distant universe, which is closely related to the first formation of stars and galaxies. So therefore, revealing this cosmic reionization history is the frontier of galactic astronomy now. So many people want to understand how this goes on. So there are two complementary ways to investigate this cosmic reionization history. One is tracing neutral hydrogen, which includes quasar spectrum and 21 centimeter emission or absorption lines. On the first day of this conference, Ms. Tsing already talked about the quasar spectrum, so I don't go to the details of this way. Another way is tracing ionized materials, which uses cosmic microwave background or first radio burst, FRBs. So let me talk about first radio burst, FRBs, later. So I will talk about first how this CMB works in constraining the cosmic reionization history in next slide. So this is again the artistic image of cosmic reionization. So as you know, CMB propagates from the redshift 1100 all the way to the redshift 0. So during this propagation, CMB will experience the Thomson scattering due to the free electrons in intergalactic medium. By observing CMB, so we can estimate optical depth of this Thomson scattering. So this optical depth is actually integration of electron density in intergalactic medium over redshift 0 to 1100. Therefore, if this cosmic reionization happens at earlier epoch, for example, very high Z, we have more ionized materials in between. That means we expect a larger value of optical depth. If the ionization happens at later epoch, for example, low Z, then we have less amount of ionized materials in between. Therefore, we expect small value of optical depth. Therefore, by measuring this optical depth from CMB observations, we can roughly constrain the average epoch of cosmic reionization. This is how CMB works. However, the problem here is that CMB can only constrain the average epoch of cosmic reionization. This is because this optical depth is already integrated over redshift 0 to 1100. Therefore, CMB is not really sensitive to the detailed structure of cosmic reionization as a function of redshift. This is the fundamental problem of CMB using optical depth. In order to overcome this problem, in our paper, we propose a new method to reveal cosmic reionization history as a function of redshift using future first radio burst. So this is my talk. Okay, let me explain. What is FRB? So first radio burst is, as Albina says, first radio burst is extragalactic burst in radio wavelengths. This is artistic image of first radio burst, which is coming from extragalaxy here. Actually, first radio burst is very bright in radio, which is comparable to the Jansky level here. The time scale of this burst is very short, which is millisecond order. So because this is new type of astronomical transient, now many astronomers are excited in FRBs. Indeed, more than 10 Nature papers have been published since 2019. Currently, these telescopes, CHIME, ASCAP, PAX, and UT-MOS radio telescopes are actively finding first radio burst. So let me introduce one unique observable of first radio burst, which is so-called dispersion measure. So this is showing a typical example of detection of FRB. Here, this is observed frequency in y-axis as a function of observed time. So as you can see, there is a straight line here. This is a typical detection of FRB. So there is a time delay, time lag of FRBs, which depends on observed frequency. This is because when a speed of light will change depending on frequency when radio emission goes through the ionized materials. Therefore, arrival time of this radio burst will change depending on observed frequency. Therefore, we will see this tilt line here. This is dispersion measure. If you have more ionized materials in between observer and FRBs, you have more time delay, which result in more tilt in this parameter space. Therefore, this is dispersion measure. Therefore, by measuring dispersion measure, we can estimate amount of ionized materials in between in the intergalactic medium. Therefore, first radio burst, FRB is very sensitive to the cosmic reionization history. Okay? So let me explain the actual situation of FRB here. As I said, when we detect FRB, we can measure this dispersion measure. So this dispersion measure is very similar parameter to the optical depth of Thomson scattering indeed. Dispersion measure is also integration of electron density in intergalactic medium over redshift 0 to the redshift of each FRB. Here, so many FRBs are now supposed to happen at very distant universe at different redshift. That means we can measure dispersion measure, this value dm, as a function of redshift. So this point is very different from optical depth of CMB. By taking this advantage of FRB, in our paper, we propose a new method to differentiate dispersion measure against redshift, which is DDM-DZ here. If we differentiate it, this value is directly proportional to the electron density in intergalactic medium, or ionization fraction of hydrogen in intergalactic medium. So that means by measuring DDM-DZ from FRB observations, we can directly estimate ionization fraction of intergalactic medium as a function of redshift, without any assumption on functional shape of cosmic reionization histories. This is the power of FRB over CMB. Okay. So next key question is that how many FRBs will be detected in future? As Albina said, fortunately, we will have a square kilometer array in future, which this SKA, which will start their science operation in 2020s in South Africa and Australia. So as you know, SKA is a big international collaboration between these many countries. So what's nice in SKA is that, roughly speaking, they will have a 2 order of magnitude higher sensitivity, and also 2 order of a larger field of view compared to the currently working normal radio telescopes. So we expect so many FRBs to be detected using SKA in the future. Actually, in our previous study, we already estimated how many FRBs to be detected with SKA, which is, roughly speaking, 10 to the 2 to 10 to the 4 FRBs will be detected at redshift higher than 6. This number is actually large enough to investigate the cosmic reionization using first radio burst. Let me demonstrate later. So for demonstration purpose, we assumed 3 different reionization histories here, which is shown by different colors here. This is the ionization fraction of hydrogen in intergalactic medium as a function of redshift here. So point here is that all of these 3 different reionization histories shows exactly same optical depth of Thomson scattering. That means using tau, optical depth, CMB cannot distinguish between these three different reionization histories. But I will say that FRB can do this. So, using the expected number of FRBs and this reionization histories, we constructed the mock FRB data, which are supposed to be observed in SKA error, which is shown here. This is dispersion measure in y-axis as a function of redshift. Each panel corresponds to the different assumption of reionization histories. So colored dot in each panel is one mock FRB data, and the mean of mock data are shown by black square. Solid line is assumed reionization histories as a prior assumption. So as you can see, first of all, there is a data dispersion along y-axis here. So this data dispersion is actually corresponding to the line of sight fluctuation of dispersion measure, which is mainly because of the density fluctuation of intergalactic medium. So as I said, DDM-DZ in this parameter space, which is actually slope of mean data in this parameter space, is directly proportional to ionization fraction. So let's assume that we will observe this mock FRB data. Then using this observed data, we can directly calculate the slope of mean data in this parameter space, which is ionization fraction. So we can reconstruct ionization fraction as a function of redshift. Okay, this is the most important figure in my talk. So this y-axis is ionization fraction, which is reconstructed from FRB mock data as a function of redshift. So reconstructed data is shown by filled and open circles here. Solid lines are assumed prior assumption on cosmic reionization histories. As you can see, this ionization fraction is reconstructed consistently. Then there are two points in this diagram. So as I said, CMB cannot distinguish between these three different histories, but FRB can do this. Even this double reionization features here can be consistently reproduced by using FRBs. Next one point is FRBs allow us to measure the ionization history as it is, because we do not assume any functional shape of cosmic reionization histories when we reconstruct this ionization fraction. Okay, so let me conclude. We propose a new method to reveal cosmic reionization histories using future FRBs, which is actually much better than CMP results. Okay, I stop here. Thank you very much.
Thank you very much. I got a question from Yenting on Slack. How do you know the redshift of the FRB host?
Okay, so we need to measure redshift from host galaxy. So we have to identify host galaxy. This is actually always difficult, but what's nice in SK is that they have a very accurate localization in SKA case. Actually, they have localization down to arc-second level. So once we detect FRB, we can immediately localize. So then we can follow up. We can do follow-up observation to identify this. That is our strategy.
Okay, more questions from, I just got a question. This is from Myunsen. Would you expect to find FRB repeaters at high G?
Okay, so, probably I don't have the slide. Actually, in our previous study, we calculated the luminosity function of FRBs. I mean, non-repeating and repeating FRBs. Then, in terms of number density, repeating FRBs are much less compared to non-repeating FRBs. So therefore, we don't really expect many repeating FRBs at very high redshift. This is simply because of the number density. But still, SKA can detect very high Z repeating FRBs, but number is very small compared to non-repeating FRBs.
Okay, more questions? One final quick one. No. Okay, so let's thank the speaker once again. And also all the speakers of this morning session. Thank you very much. And because there are some questions that could not be covered during